The thing that holds the International Space Station together weighs 450 metric tons. 450 metric tons of aluminum, titanium, steel, and wire, orbiting 400 kilometers above your head right now, traveling at 28,000 kilometers per hour. Every single gram of that had to be dug from the ground, refined, machined, tested, and launched off a planet. Forget the blueprints. Forget the factories, the engineers, the supply chains. Imagine all of it gone, the station, every satellite, every piece of orbital hardware, and humanity wakes up with nothing but raw stone and the memory of what we built. Getting back to orbit from that starting point begins with a metal that not long ago was more expensive than silver. Before a single kilogram reaches space, you'd need to solve a problem that took our civilization most of the 19th century. Aluminum. It makes up roughly 8% of Earth's crust, yet almost never exists in pure metallic form in nature, because it bonds so aggressively to oxygen. Instead, you dig up bauxite, a rust-colored ore, and begin a chemical separation that took the best chemists alive decades to crack. Napoleon III reserved his aluminum dinner service for the most honored guests at imperial banquets, while visitors of lesser rank ate from gold and silver, because aluminum cost more. In 1884, engineers capped the Washington Monument with a 100-ounce pyramid of pure aluminum, because it was one of the most expensive materials they could procure. Then, in 1886, it happened twice at once. Charles Martin Hall, a 22-year-old working in a woodshed in Oberlin, Ohio, and Paul Héroult, working in France, independently discovered the same electrochemical process within months of each other. Same year, same answer. Neither man knew the other existed. Within a decade, aluminum went from a luxury metal to the material in your kitchen drawer. Rebuilding from nothing, you don't get that discovery until you've already built large-scale chemistry, electrical generation, industrial mining, and furnaces capable of sustained extreme heat. Generations of work before you touch a single launch vehicle. That gets you structure. What keeps that structure alive in space is a different category of problem entirely. The ISS doesn't carry oxygen tanks. Oxygen is made on board. Water molecules are split by electric current. The oxygen goes to the crew, and the hydrogen vents out. Everything else is recovered: moisture from the air, condensation from cold surfaces, even urine processed through a system so thorough the crew calls the result yesterday's coffee. Around 93% of all water aboard is recovered and reused. Any gram that isn't captured is mass that has to be launched from Earth, where reaching low orbit costs tens of thousands of dollars per kilogram. Life support on the station has no backup. It's the only plan. Rebuild from scratch, and you'd need centuries of chemistry, biology, and mechanical engineering just to conceive of a closed-loop life support system, let alone trust 8 people's lives to it, 250 miles off the ground. That handles survival. Getting there at all is the problem nobody mentions first. Orbit isn't up. This is where most people's intuition fails completely. Throwing something high enough isn't the hard part. You could deliver enough energy to lift a mass 400 kilometers above Earth's surface, and gravity would still pull it back down in minutes. Sideways speed is what you actually need, so much of it that as the object falls toward Earth's curved surface, the surface curves away beneath it faster. At orbit, the station moves at roughly 28,000 kilometers per hour. Not 28,000 kilometers high, 28,000 kilometers per hour sideways. To deliver even a single module the size of a school bus to that velocity, a rocket has to carry most of its own mass as propellant. Assembling the ISS required more than 40 separate missions. 37 of them were space shuttle flights. That's the physics. No material substitution solves it. No clever engineering sidesteps it. Anyone rebuilding from zero would have to rediscover the rocket equation, then spend decades learning to produce propellant at the scale and reliability that orbital launches demand. And that's still not the hardest part. 5 space agencies, 15 nations, 13 years of active construction. Assembly started with the Russian Zarya module, launched in November of 1998. Structural work finished in 2011. $150 billion across the program's lifetime. 450 metric tons orbited and assembled by astronauts in spacesuits at 28,000 kilometers per hour, guided from the ground by thousands of engineers running on software written by thousands more. Now pull all of that out from under the project. Aluminum smelting wasn't cracked until 1886. Before that, you don't have the primary structural material. Air breathability inside a sealed module depends on electrochemistry and biology that accumulated across nearly 2 centuries of scientific work. Orbital mechanics that tell a rocket where to aim were developed mathematically long before the first rocket flew, but applying them to actual flight took national space programs that only emerged from the wreckage of a world war. You aren't rebuilding a space station. Every step backward from orbit reveals another step that has to come before it. Humanity has been continuously aboard the ISS since November 2nd, 2000. A human being has lived in that structure every single day for more than 2 decades. That's the number that doesn't show up in any budget estimate. Not $150 billion. Nor 450 metric tons. Keeping people alive up there required knowledge accumulated across so many generations, woven so deeply into supply chains and institutions and manufacturing processes that most people will never notice, that the path back to orbit doesn't start on a launch pad. It starts in a woodshed in Oberlin, Ohio, and before that woodshed, it starts somewhere even smaller. Scrap metal was always there. We just had to spend 2 centuries figuring out what it was.